let's just take it back for a moment. Okay, when we're looking at polynomials, we want to factor them. Oftentimes we're doing it so that we can find solutions for the given equation. If I was going to look at something like x squared plus 6x plus 8 maybe equals 0, I want to apply that zero factor property. So again, the way that I would proceed is I would look at the very, very last term, 8, and then I'll look at all the factors that would comprise 8, such as 1 and 8, 2 and 4. Also, the negatives, I might also want to consider them, such as -1 and -8, and -2 and -4. Then when we look at the internal mechanism, what happens is we would see, okay, what would actually sum to the linear term, the thing right there in the middle, value of 6, and we'd make the observation, okay, 2 and 4, that's going to work. Consequently, when we factor the quadratic, it will be x plus 2, x plus 4. And then we apply the zero factor property. We have our factors, take it, decouple it. We're going to have x plus 2 equals 0, x plus 4 equals 0. And then from here, we would solve. And the values you get down here in the very end, these are the solutions, but they're also referred to as the roots, or they're also known as the zeros. And we saw this too when we're looking at the quadratic formula. If you can use a quadratic formula, you can also, you're going to find the roots here in the end. You also get -4, and you also get -2. Now, what's really important about the roots is whenever you take the value and you plug it into a given function, like if you were plugging -2, it will be a root if and only if you get 0 out of it. In other words, it annihilates the polynomial. If you don't have this, I'm sorry, it's not a root. I don't know what it is, but it's not a root. If you were to, for instance, plug in 1, or if you take this to be f of x, you're going to get 1, you're going to get 6, you're going to get 8. Okay, and that's not 0. It's not a root. Whenever you have a degree 2 polynomial, you're always going to have 2 roots. They might be repeated, they may not be repeated, but you're always going to have 2 roots. If you have a degree 3 polynomial, you're going to have 3 roots. They can be all repeated, or they can be distinct, or maybe 2 are repeated, 1's distinct, but you're always going to have 3 roots. You can kind of see where this is going. You have a degree 4 polynomial, you're going to have 4 roots. So based upon the degree of the polynomial indicates the number of roots you will have for that given polynomial. Whenever you factor a polynomial, it will always, doesn't matter if it's a Monday, doesn't matter if it's a Tuesday, doesn't matter if there's a comet outside that's from the interstellar, it does not matter. It will always, always factor as x minus the root. Always, when you're factoring a polynomial. So the reason why you plug in the value, this thing called a root, you get 0. What happens when you plug it in right there? You get 0. Okay. That simple observation has a wealth of information in it. It tells you exactly how to factor polynomials. If you can find a root, you got it. You can factor it. Let's just say if you have some kind of polynomial, f of x, and I'm not going to tell you what it is, but I'll tell you what it does. And what I want you to do is generate a polynomial which will mimic that behavior. Okay. Suppose that we're going to have roots right at 1, 3, and 5. Well, I know the secret of how to factor a polynomial. Doesn't matter if it's Monday or Friday, so it does not matter. The way that's going to factor is x minus the root. So I'm going to have x minus 1, x minus 3, x minus 5. That right there will be a polynomial which will satisfy the condition so that 1, 3, and 5 are roots. It's not the only polynomial that works. You can have other polynomials. You can plug a 5 in front if you want to, or you can make it a 15 if you want to. But whenever you plug in 1, 3, and 5, it will always be a root. Because again, it's a root because we have x minus the root. That's right here is going to be a factor. There are other polynomials that we can also pick that also would work. You know, I can pick another one, such as put a square right there, and I can put a cube right there. And whenever I drop in 1, 3, and 5, it's still going to be a root, and it's still going to churn out. Well, there's another matter when we're talking about roots, which is also really important, and it's known as algebraic multiplicity. And you probably remember it as just simply multiplicity. Now we call it algebraic multiplicity because truthfully there's more than just one type of multiplicity. There's other types of multiplicities out there. But for our purposes, when we say multiplicity, we are just referring to algebraic. And what that means is, when looking at the algebraic multiplicity, it's just the number of times that it's going to occur as a root. And let's say for a moment that the algebraic multiplicity, or the multiplicity of 1 is 1, and multiplicity of 3, let's say it's going to be 2, and maybe this one, let's just say it's going to be 3. It's not going to make a lot of sense for me to say that the multiplicity of 3 is going to be 2. That's nonsensical. That's ridiculous. That doesn't make any sense. And you know, if you say the multiplicity of 5 is 3, okay, we're just making things up, it seems like now. So to safeguard ourselves, to make sure we don't make this mistake, because guys, it is a very common mistake. I see it all the time. I know what students are trying to say when they say this, but they're not saying it properly. And I am sad to say that yes, there is grammar in mathematics. Here it is right here, at least part of it. This doesn't make sense. This violates laws of logic. So to safeguard ourselves so that we don't make those fallacies, what I'm going to say is the algebraic multiplicity of 3 is going to be 2. So I'm just going to kind of introduce this as a function. The algebraic multiplicity of 5 is going to be 3. And the algebraic multiplicity of 1 will be 1. Okay? And all that means is the number of times this is going to be a root for the given polynomial. Okay? The way that you would express this, or the way that you see this in terms of a polynomial, it is simply nothing else than the exponent. And that's it. So if I have roots with multiplicities of 1, 2, and 3, what that would then indicate is, again, it's a root, so I know it has to be x minus 1, because otherwise, guys, it's not a root for the polynomial. It must have that structure. It must have that form. X minus 3, and then x minus 5. Then all you do is take the algebraic multiplicity of the roots, and you power them up. Just like that. And that's the way that it always works. So if the multiplicity of 1 is 1, that's your factor. And if the multiplicity of 3 is 2, that's your factor. And likewise, the multiplicity of 5 is 3, so that's your factor right there. Okay, now there is a wealth of information actually stored within the multiplicities. And we'll see that as we keep going through looking at polynomials in more and more detail. But one of the things that we can observe right now really quickly is, what if I was going to add these up? Okay, and I would get 1, 2, and 3. I would get 6. And if I was to invest the time to really crank this thing out, okay, first off, this is a quadratic. And with a quadratic, it has to be something like x squared. And here's a great math word for you guys: stuff. What kind of stuff? The right stuff. Okay, x to the third power. Then we get some more stuff. And over here, you would have x and then stuff. Okay, that's just one in this case. But if you were to expand out, distribute, x times an x squared would get you a, x to the third. And then you would get x to the third and then more stuff. And what would happen then if you take a cubic, multiply it by a cubic? You get x to the 6 plus stuff. In other words, if you were to cross these out and multiply through, what's the degree of the polynomial? Where does 6, where have we seen that before? It is the summation of all the multiplicities of your roots. If I want to determine the degree of the polynomial, and if I don't really know what it looks like, I can decipher it fairly quickly by taking the sum here. That seems like a pretty good, question on an exam, doesn't it? Where I give you the multiplicities of the roots, and I don't tell you what the degree of the polynomial is, and you got to figure it out. And the way you'd figure it out again, just add up the sums. Sum up all the multiplicities. Let's say if I have f of x, and again, it's going to be a polynomial, and I'm not going to tell you what the polynomial is, but I'll tell you what it does. And I'll give you a little bit more information too. It's a polynomial with real coefficients. So if I was to look at the polynomial, in general, if I was to open this thing up, this would be something like a sub n, x to the power of n, a sub n minus 1, x to the power of n minus 1, all the way down as far as you need to, a2 x squared, a1 x, a naught. Every single one of those coefficients, a naught, a1, a2, every single one of these values, they're going to be real. And all those really represent is just something like 2x squared plus 3x plus 1. A2 is 2, A1 is 3, A naught's 1. I just can't really say A, B, and C like we typically would when we're looking at a quadratic, because eventually I'm going to run out of fingers to count on, and I'm going to run out of letters eventually. And when I get to maybe like degree 26, okay, I'm fine. Degree 27, okay, I'm out of letters, really. I really would end way before then too, but so we use subscripts. At least you'll see them represented as subscripts. It's just a way to index the values. Is it the constant term? Is it the linear term, power 1? Is it the quadratic coefficient, power 2? Is it the nth term, power of n? That's all it represents. So again, we're going to assume that we're going to have real coefficients. Okay, that's important. Let's say that I have a polynomial and I'm going to have roots of 2, and let's get a little complex. 1 plus I. And I want to develop a polynomial which will have that structure, which will have those roots. And answers could definitely vary. So I might want to hammer it down a little bit more and say, okay, the multiplicities of these roots, so this one, let's say this is going to be a value of 3, and let's say the multiplicity of 1 plus I, let's say it's going to be 1. Our objective is to find a polynomial, construct a polynomial, which has these roots, and the coefficients must be real. So it's a puzzle. I got to put this thing together. And like with any games, where it's a game of hearts, if it's a game of spades, it does not matter. You must follow the rules of the game. If I'm factoring, one of the rules of the game is it's always going to be x minus the root. Otherwise, if you do not have that as a factor for your polynomial, it's not a root. Okay, so again, I know that 2 is going to be a root, so I know it's going to be x minus 2. I know the multiplicity is going to correspond to 3. So that just means take this and power it up. Okay, and then likewise, even if it's complex, you do exactly the same thing. You say x and then minus the root, which is going to be 1 plus I. And then if you power it up to the first power, okay, it's just You can say this, or you can just simply leave it off. If I was to expand out for the moment, to put this polynomial, which is in factored form, into expanded form, I might want to apply like the binomial theorem or something here to really crank this out. Okay, and then multiply it by this factor. If you were to start combining all your like terms, take the quadratics, add them together, take the linears, add them together, you're going to run into a problem very quickly. And the problem is, we're trying to generate a polynomial which has what kind of coefficients? Real. What kind of coefficients do I have here? Not real. They're complex. So here's the deal. Whenever you're working with polynomials and you're talking about polynomials with real coefficients, this is part of the story. This is not the full story. What happens is you're going to have roots, if they're complex, they're going to arrive in conjugate pairs. This says 1 plus I is a root, and it's given. It did not say that I, or negative I plus 1, this is also going to be a root, but that's implied. So you have things sometimes which are explicitly stated. I'm telling you flat out exactly what it is. You don't have to read between the lines. Sometimes, like you know in life, guys, you got to read between the lines. Literally, in this case, read between the lines. If you have a plus bi, if that's a root, then so is its conjugate. And sometimes you might see it denoted with a little bar on top. And all that means is take the sign and flip it in front of the complex component. And they're going to arrive in the exact same distribution. If this occurs once, this can't occur twice. This also has to occur once. So if this multiplicity is 1, so is this one. And if this multiplicity is 4, so is that one. So it's one of those things you just have to look for and look into it. And this happens every single time on every exam that I give on the subject. Students will always say this, and they forget about the complex component. Don't forget about that. Okay, if 1 plus I is a root, then 1 minus I is also a root, and the way that I factor, it's always like that. So we have x minus 1 minus I. That's the root. And if it is raised to the 4th power, you raise it to the 4th power. Okay, now that's part of it still. We got that locked in place, so we're not really talking like a degree 4 or degree 7 polynomial. We're talking something much, much higher. Okay. I have to make sure, and this is important, that the roots are what kind of values again? Or excuse me, the coefficients? They gotta be real. What's the problem that I have? That's not real. I can't have that. So I got to do something with it. But what I don't want to do, okay, I can do it, but it's pretty crazy. It really is. I don't want to take this and expand out. That's nuts. Like we saw there a moment ago. Okay, it will work, but it's way too much work. It's too complicated. And truthfully, a lot of things that you want to do is you want to keep things in factored form. Factored form has more information embedded within it that you can retrieve than you could when it's expanded, at least for our purposes. Okay, so here's the deal. if I want to do this, I got to be a little bit more clever. And we can use properties of exponents to help us in this endeavor. If I have a to the fourth, b to the fourth, like I have right here, I can take it and recalibrate it using that property of exponents. And that will get rid of the 4. So again, we identify the problem. There's no way I'm going to power something to the 4th power. That's complicated. So how do I work around it? Power it up. Properties of exponents. Okay. Then the next thing is, I just want to expand out just a little bit. Not too much, just a little bit. Okay. Again, I got an option. This will work where I can take this term, multiply it through. Okay, that will definitely work here. I probably want to drop down the parentheses first before I do that. Distribute the negative. But I'm going to get 9 terms in the end. Okay. Before I'm prepared to invest that amount of time, what I want to do is I want to be a problem solver. I identify the problem. I have an option. I'm not prepared to go down that path quite yet. I want to see if I have a nice pattern that I can use that's going to help me in this endeavor. Okay, guys, it's kind of the difference between looking before you leap or just going through the grind and hoping that you get it done and not really sure what's going on. One pattern that I do see here, if I just start collecting all the real terms together, like the x and the 1, could it be right before my eyes the hippopotamus property? That right there, A minus B, isn't that what we call it? We call it the hippopotamus property, didn't we? Still not catching on? Okay, I'm gonna write my congressman and see if I can get this changed. Maybe in a few weeks I'll write them. What's a better name for this? This property that keeps popping up like a whack-a-mole. You can't get away from it. Difference of squares. So when I go through this process, we'll have x minus 2 raised to the 3rd power. We'll have x minus 1 squared. Because again, take the a, and this is a, minus, take the b, and square it. And again, b is going to be I. Don't forget about the 4th power. And what happens when I see an I squared? I replace it with -1. Do I have any more complex imaginary numbers up here anymore? No. They've gone away. They're not here anymore. Okay, now, the next thing is you can take this and just expand out just a little bit more, tidy it up. We'll have x squared minus 2x plus 1, add it to 1, thereby giving us in the very, very end, x minus 2 quantity cubed, x squared minus 2x plus 2 raised to the 4th power. And what I don't want to do now is take this and expand out. Okay, I can, but I know I'm going to get a real coefficients for my polynomial now. There's no point in doing so. Okay, just remember, it is better in a lot of cases to keep things in factored form for as long as you possibly can. And there is no significance as taking this polynomial and expanding out. I don't really need to do that. There's more power here keeping it in factored form. Okay, so when you're looking at complex roots, you got to remember they arrive in conjugate pairs. And if this is a multiplicity of 2 or 3 or 4, so is the other one, 2 or 3 or 4. Don't forget about that. And the trick here is to use properties of exponents like a crescent wrench. You just kind of open this thing up, pry it open, get that 4 off these two pieces, then apply the difference of squares identity where you take A, right, for this part, and you take B for the next part. A squared minus B squared, no more complex number. And then just tidy it up here in the very end. And that's a great answer. We're kind of getting a pretty good idea now of how roots interact with polynomials, how they interact with factors. But let's say for the moment, if I gave you a polynomial and someone did us the disservice of taking this and expanding out, and it is my job to factor this. The way that I can factor a cubic or a quartic, degree 4, or a quintic, degree 5, really is an extension of how I can factor a quadratic. There are different ways how I can go about this, and it will work. I can use a box method, I can use that cross method, but that does not help you anymore when you get to degree 3 or degree 4. So if you learn that, you're going to have to learn something else. Or if you learned the way that I taught you, because I knew what was coming, if I just looked at the factors and I saw how the factors interact, I can crank this out fairly quickly. And the way that I factor a degree 3 or a degree 4 is the exact same way that I do down here. And we have something called the rational roots theorem. So first off, it says the word rational. So it would be irrational not to talk about rational numbers. Remember what a rational number is? Something of the form P over Q. What's a root? I forget. You take it, you plug it into a function, it annihilates. See, there's meaning behind the words. They're just not randomly picked. So again, if you're struggling with, okay, I'm not sure what this word, this phrase, what this means, dissect it. Rational number, root means this, so I gotta have this. So this is a theorem that kind of indicates, kind of steers you in a good direction on how to find these roots. Okay. So the theorem, what it states here is, what you're going to do if you want to find these rational numbers, remember things like 2/3, 4/3, or something like 2 or even -1, not pi or square root of 2, is you're going to be looking at this term here and that term there. Look at the leading coefficient, look at the constant at the very end. Then you are going to be looking at every single one of the factors that will divide into it. And we'll say factors for a sub n and factors for a naught. And then once you have all these factors, you're going to put them together. And these are going to be all your p values. These are going to be all your q values as you form the rational number. I look at the leading coefficient. I look at the constant. I look at all the factors. Look at all the factors over here. Okay, but don't forget about there are also negatives. -1 also divides 6. -2 also divides 6. But keep the negatives to the very end. It makes it a little bit easier. But put it all together. Take your p values and divide your q values. And it's helpful just to write out the list for P, and then come through here and divide out by Q. In the end, simplify it down, 1, 2, 3, and 6, and don't forget about plus or minus. Those right there are your possible rational roots. If this polynomial, if it has a rational root, guys, that's one of them right there. It may not have a rational root, and that does happen. Now, I can have things such as x squared minus 2. That doesn't have a rational root. It's irrational. Square root 2 is the only thing that's going to work, or negative root 2. But if it does have a rational root, that polynomial's got to be one of those. Okay? I got to factor. I got to find the roots. And I note that all the coefficients, they're integers, so I can look at the rational roots theorem, look at the leading coefficient. Now it's just an a sub n, the very first one. Look at the last coefficient, the constant term. And although, yeah, it does say -6, I'm not going to worry about the -6. I'm just going to say 6. And then I'm going to look at every single factor that I could generate. Okay. Things that will divide into 6, 1, 2, 3. Does 4 divide into 6 evenly? No, so skip that. How about 5? No, skip that too. 6. Come over here and look at all the factors that would comprise 12. Okay, it's a composite number. It's not a prime number, so yeah, it's going to take a little more. But we're going to have 1, 2, 3, and okay, 4 works now, but not 5. 6 will work, not 7, not 8, 11, 12. 12 works. Right there. Then it's a big long list, but you're going to form all the rational roots that you can possibly get. Okay, again, because it's so big, what you can do, you can be a little more systematic, more strategic about it. Take the list and just maybe list it out, 2, 4, 6 times. Then take your a sub n and divide. Do it for this one, do it for this one, then do it for the rest of them. Now, after you form your P and Q, go through the lists, simplify it down a little bit more. 1 over 1, okay, that's 1. 2, 3, 6. Get a half. But what's 2 over 2? It's 1. That's already been included in the list. Skip over it. Grab the next one. 3 halves. Okay, what's this one? That's 3. Was that already included in the list? Okay, so skip over that one. You get a third, 2/3. What's that one again? It's 1. So skip over that one. What's that one? Okay, it's already been included, so skip over it. And just keep going through the list like this. Okay, here you can get a 4th. What's that? That's a half. It's already been included. 3/4. What about this one? Okay, that's going to be 3 over 2, but look at that. So I don't want to have repeats, just once is good enough. Okay, a 6. A third's been repeated up here, so we can get rid of this one. That's a half, that's 1. And we're left with 1 over 12. Okay, a 6, a 4th, and a half. Okay, so there it is. These values up here are your permissible rational roots, plus or minus. Don't forget about the plus or minus. Tack that at the very, very end. Don't do it over here. It's too convoluted as it is. Just at the end say plus or minus. Okay, so I say possible because that's a whole lot of roots. This is a degree 3. I only need 3 of them. I don't need all those. But if it has a rational root, it's going to be one of these. Okay, I just not for sure which one it is quite yet. And truthfully, guys, this is comforting. Because if I had to factor this without having this compass, this way to guide me, how would you do it? I mean, you're pretty much stuck. Well, what do I know about roots? I know it annihilates polynomials. I know when you take it, you plug it in, duck and cover, kaboom, 0. Okay. But how can I go about this process, to find 0? Okay, I can definitely take each one of these and plug them in, plug in 1, plug in 2, plug in 3, but that's going to get very convoluted fairly quickly. So instead of just taking it and plugging it in, we can invoke the whole entire idea of synthetic division. First term drops, and if the last term here, if that's 0, congratulations, you found a root. That's the objective. That's what you're looking for. Okay. Now, the list here, it's pretty long. I grant you that. There's a lot of information up here. And if you're on an exam and you got to factor a cubic, something of this form, time is of the essence. So again, guys, you got the option. You can just get into the grind and not look before you leap and just hope that it comes in time, or you can use some strategy. Strategy is going to take this list and half it, if not, reduce it by more than a half. Here, I got some really big numbers, right? And I got to get to a really small number. It would not make sense for me to put a 6 right there. Because if I put a 6 right there, what's going to happen? I get a really big number next. Do I have enough time? Do I have enough coefficients for this to go back and forth between positive, negative, and collapse it down so I get 0? No. So I can already see before I go through the calculation, that's not going to work. Use strategy to help you in this endeavor. Also, let's say if all these values, if they were positive, would it make any sense at all to pick a positive number and put it here? No, it wouldn't make sense because there's no way that I can get down to 0. And that will take my list and half it very quickly. So instead of looking maybe at 20, maybe looking at 10. And then if the numbers are too big, you half it again. Maybe we're just looking at 5 or 4 values to check. If you bring strategy, number sense to the game, it makes these problems easier. If you don't, and you just look at the grind, what is going to happen is you're going to be on the exam, you're going to say, that's the hardest exam I've had in my whole entire life. I didn't have time to finish it because you're not doing it the way you should be doing it. Bring strategy to the game to help you out. So I got to get this number, I got to knock it down pretty quickly. So that tells me I'm probably looking at maybe like a half or negative a half. I just want to kind of, try something and see what's going to happen. So a half times 12 will get me a value of 6. Okay, I'll get 26. Okay, I'll get a value of 13. Take these two and add them up. I'm going to get 12. A half times 12 gets me, wow, I got it. Did I have to check everything? I could have. But how much time is that going to take me? A whole bunch of time. And if I did that, that's probably the only question I may not even answer it, but it's probably the only question I'm going to see on the exam. So bring strategy to the game. Just don't go through a grind. Look before you leap. And I know that whenever I plug this into the function, I get 0. So I know how this thing factors. X minus the root. It always factors like that. It always will. And if this is a degree 3, I just generated a degree 2 polynomial. So now we're left with 12x squared, 26x plus 12. And I do see a common term amongst all 3 of these. 2, factor it out, maybe put in front. So we have 6x squared, 13x plus 6. So we took the cubic and we reduced it down to a linear times a quadratic. And then from here, do you think you might be able to figure it out? Yeah, absolutely. It seems like you're probably going to need something like a 3x and a 2x. And just see how it's going to ride. Maybe a 3 here and maybe a 2 there. We'll see if it works. So you have 6x, 9, plus 4 more gets you 13. And if you want, take the 2, distribute it, your choice, your call. But there's the factored form. Wow. Guys, we can factor cubics now. And we can factor degree 4, we can factor degree 5. There's no stopping us because we know how things work. And by knowing how something works, we can hit more complicated problems. All right, that's all the time we got. You guys have a great day. See you next time.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.